All right, guys, this is part 3 of our hypothesis testing with z-tests lecture. In this one, I want to go through an example with some data. And then in the last lecture, we'll go through, or the last video, I should say, go through yet another example with some data to really sort of hammer this stuff home. All right, so remember, z-tests are a form of hypothesis test that you can perform when you have a sample average, right? You know something about a sample, you know the sample size, and you also know some information about that population. Specifically, you know the population mean and the population standard deviation. Without that information, you cannot perform a z-test. It's just part of the z formula. Okay, so in this example, we have a hypothetical scenario where 97 students at the University of Michigan Dearborn take a test, okay? Their average on this test was 156.11. Now, this test has been given nationally, and so we have information on the population average and standard deviation. And so that's given in this problem, right? The mean of 156.5, standard deviation of 14.6. Now, notice I have really streamlined this problem. I didn't put a whole lot of context, a paragraph describing the scenario, but you should be able to see those as well and be able to extract the relevant data from more of what you might consider like a word problem. And the next example that we go through in the last video will be more akin to that. Okay, so I always like to take the information out of wherever it is and place it to the side in a location where all of the relevant values, all the statistics and parameters that I need are right there, easily obtainable. So what do we know in the problem? What can we do? What can we write to the side? Our population mean 156.5. Our population standard deviation, 14.6. That's how the population performs on this test and the variability of that. Our sample of 97 Dearborn students performed an average of 156.11. These are highly similar, that 156.5 and then 156.11. We're simply asking, are they different? Are they different enough that we would say that there's a statistically significant difference and that that difference is unlikely to have occurred in 5% or less of the cases if chance alone were operating, okay? So 6 steps of hypothesis testing. Let's run through them all. Start with the first one. Population, distributions, assumptions, okay? What are our populations in this case? Well, we know that we're comparing Dearborn students. The sample of 97 should be, because we know nothing else about this, a representative sample of that larger population of Dearborn students. What we're asking is whether or not that population of Dearborn students is essentially the same population or highly identical to the national population, or if they are different in some way. So our comparison population then would be all students nationwide, right, who have taken this test. I can generalize after this to people who haven't taken the test that we'd see a similar difference. So populations, those are our populations. What's our distribution? Well, we see we've got a sample mean and a population mean. We're going to be comparing one mean to another to see if they're far enough apart to say that they're statistically significantly different. And so it's a distribution of means. All those possible values of the sample mean. So if we took a different sample of 97 students and then a different sample of 97 students, we kept doing this over and over and over and over and over again, that hypothetical distribution of all the possible values of the sample average is that distribution of means. That's the one we're going to be using for our comparison distribution in this example. Also, it's the only one you know at this point, so that makes it a little easier to guess. Test and assumptions then. Well, we know population information, right? Population mean and population standard deviation. We have sample mean and sample size, which means we are in the world of a z-test, which means the assumptions then are that the data are interval, right? It looks as though they are. There'd be no reason to doubt the scores on a test being interval in nature, right? We're going to hope random selection of these 97 students and not 97 engineering students or 97 history majors or whatever it happened to be. And then we know that our sample size in this case is well above 30. So central limit theorem says that that distribution of means should be normal, even if the underlying distribution of raw scores is skewed in some way. We also know that these are fairly robust tests, so we can kind of bend the assumptions a little bit. If it wasn't random selection, for example, and it was all engineering students, then we would just have to say that engineering students did or did not differ from the population average. We might not be able to generalize to some of the other colleges or majors. And so remember, these assumptions are bendable, right? Not quite breakable, but fairly bendable. Okay, step 2 then is state the null and research hypothesis. This is pretty easy. We can do it in symbols first. We haven't really talked about hypotheses and symbols, right? But the null hypothesis is represented as H sub 0. And the null hypothesis in this case could be that the population 1 is equal to population 2, right? Population 1 could be our UMD students, and population 2 could be the nationwide, or swap them, it doesn't matter. Or it may be that if we're predicting specifically, we think on our research hypothesis that UM Dearborn students are, say, better prepared, right? And we think that population 1 will be better than population 2 in our mind. That's what we think is going to happen. Well, then our null hypothesis would say the opposite, and it would say that population 1 would be equal to or lesser than population 2, right? The UM Dearborn students would score equal to or lower than the population in our null hypothesis. So then our research hypotheses, which get the H1 designation, or if we have multiple hypotheses, it'll go 2 and 3 and 4, and so on and so forth, would either be that population 1 is greater than population 2. Remember, we're just talking in symbols, that's why I'm saying it this way. Or that population 1 would not be equal to population 2. So it depends a little bit on how you frame your hypothesis, what exactly your null hypothesis would be. Is it that you have no difference versus a difference? Or is it that you have greater than versus less than or equal to? Right? Again, it just depends on how you frame that hypothesis. So I always want you to do this in words too. So on the exam, when I say, tell me your hypotheses in this example, tell me your hypotheses in the context of these variables, however I word it, even if it's just what is the likely hypothesis, this is what I want to see, the words, okay? I just want you to be able to think in the symbols as well. So the words, the mean of population 1 will be less than or equal to the mean of population 2. And more specifically in our example, the mean of UM Dearborn students' tests will be less than or equal to the mean of the nationwide average on this test, right? That's one way of framing that null hypothesis. In this case, it's because we would have a directional hypothesis. So look at H1 in the bottom left of the screen here. It says UM Dearborn students on average will be greater than the nationwide average, right? Greater than. Not different from, but a specific direction of difference. In this case, saying that Dearborn students' average would be higher than the nation. Because that's a directional hypothesis, our null hypothesis is the other direction, right? It's saying they'll be either be equal or the opposite way. We don't have to have directional hypotheses. And in fact, from a standpoint of testing them, we're always going to sort of work with a non-directional hypothesis, even if we have to frame the hypothesis more directionally. So I'll elaborate on that as we get into these. But a non-directional version of that hypothesis would be something like the average of UM Dearborn students will be different from the average of the nation, right? The null hypothesis then being that the average of UM Dearborn students will not be different from the average of the nation on this particular test. So directional, non-directional hypotheses, hypotheses in symbols, hypotheses in words, right? Make sure you sort of know how to think about your hypotheses in really, I guess, all of these ways, and start to think about the difference between a directional and a non-directional hypothesis, because it's about to become relevant. Determine the characteristics of your comparison distribution. Okay, so here are the values that we already had. Population, the mean of the population was 156.5. The standard deviation of that population was 14.6. The sample average was 156.11, and the sample size was 97. Now, remember that the z-statistic formula uses standard error, not standard deviation, because the variability of that comparison distribution is different from the variability of the raw scores. So you have to take the standard deviation of that population, right, little sigma, the light blue number 14.6 up there, and divide by the square root of the sample size. Sample size in this case is 97. Thank you. So place 14.6 in the numerator, square root of 97 in the denominator, carry it through, you get a 1.482, or basically a 1.48. So now we have our standard error. Now we have the comparison distribution characteristics, because we know that a population mean, the 156.5, is equal to the center point of that comparison distribution. So, moving forward then, we need to determine our critical values. This is step 4. Now, we haven't talked about this quite yet, so let's talk about it now. In behavioral sciences, we take an acceptable risk of 5% of the time when we declare our hypotheses to be supported and the null hypothesis to be rejected. It's okay if it would be 1 in 20, if 5 out of 100 times we are wrong. And that's largely because our hypotheses don't have nearly as grave an implication as, say, whether a vaccine is likely to kill or save somebody. In those cases, medical researchers would use a different cutoff value. Instead of taking a 5% risk, the p equals 0.05, they might take a 1 in 1,000 risk, a p equals 0.001. Whatever the risk is, we're going to use that percentage to determine our critical values. So, because we're going to work with a hypothesis that says Dearborn students are different from the national average, a non-directional hypothesis, that means when we place that z statistic, so to speak, of our sample mean relative to the population mean, right, the national average, it could potentially be above. It could potentially be below. That is, our average could end up being above or below the nationwide average, which means we have to think about what that 5% really represents. We need to make sure that that 5% risk is divided equally across both tails. So, where does that get us for a cutoff value? When we try and determine what z statistic we need for a cutoff value, we have to think about what percentage of the distribution we need to be into those tails or tail. In a two-tailed test, where our sample mean could be either above or below the population mean, we need 5% of the whole distribution to be in those tails. And that means that if our z statistic is farther than that cutoff, then it is so far from the mean that it is in the smallest 5% probability in one direction or the other. So, to be fair to both sides, of course, you divide 5 by 2, and you need 2.5% in each tail, which then means if you're to find your cutoff value, think about the way your z-table is set up. Z-table tells you the percentage of the distribution between the center and that z. We're trying to find the z statistic that represents 2.5% in the tail, which means we want to look up the z statistic that has 47.5% between the mean and z. So you just go into your table, find that value, right, that represents the 2.5% in each tail. Remember, the distribution is symmetrical, so if it was a 1.96, which it would be for this cutoff value, then you would also have a negative 1.96. So our cutoff in this example would be a plus minus 1.96. And if you looked in your z-table, you would see that that 1.96 corresponds to roughly 47.5% between the mean and that score. Okay, so that's how we get to this particular cutoff value. If you had different cutoff values, you'd simply determine the percentage between mean and z for that cutoff value, and then go into your table with that particular value. So let's look at the table real quick to sort of see how this would work, right? 95% divided by 2 leaves 47.5% in that center, which means we're looking for the percentage that corresponds to that 47.5%. You can actually see it directly in the table here. You have to scan through the values. They sort of increase as you go. When you find it, find the z statistic then that corresponds to that, red squared value, and you find it in this case to be 1.96. Because it's a two-tailed test, because we're using a non-directional hypothesis, it's a plus minus 1.96, okay? That means our z statistic could be less than negative 1.96 or greater than positive 1.96. Either of those would take it into the tails of the distribution. So now's a good time when you're in the problem to draw the distribution. Place the zero line. Place your z statistic of, in this case, 1.96 and negative 1.96, and then shade in the tails of the distribution. Now what we're going to do is see if our z statistic that we're going to calculate next falls into one of those shaded regions. Okay? So, next part of the example, get that z statistic. This is our formula. We've already calculated standard error in a previous step. We already know sample mean and population means. We plug all of that in. Probably not going to be a very big difference because you can see how small the difference is between the sample mean and population mean. But what's our z statistic? Negative 0.26. We are below the population mean, so we have a negative z statistic. It sounds like we are very close to that population average, so if we visualized it, negative 0.26 is really close to the center of that distribution. It is not, in fact, less than negative 1.96. It does not fall into one of these tails, and visualizing really helps here. And so when we make a decision, we would say that, no, we fail to reject the null hypothesis. The average test score of Dearborn students does not differ from the average of the nation's test scores in that particular year, right? And then we would report the Z information and the p-value, but I'll show you that in a subsequent example, okay? One more quick point before we cut this video is about sample size. So you might say that if sample size could be 30, and that meets the central limit theorem, why ever go above a sample size of 30? Well, one reason could be that sample size actually does matter. Sample size is not just going to get you a more representative group because you're literally capturing more of the population, but it also has a direct mathematical influence on your calculations. So it should make sense that if our difference does truly exist in the world, so the Dearborn students really are different from the nationwide average, or people who drink coffee while caffeinated are more likely to remember things than people who are not caffeinated. If those differences really do exist in the world, then the greater your sample size, the greater the probability would be that you'd see that difference, right? Because you'd eventually capture enough of the individuals that were truly represented that difference, and you'd be able to see it. So from a philosophical standpoint, it makes sense that sample size would have an effect on finding a significant effect. I don't know if you guys can hear my dog. One dog's in heat, the other dog's horny as hell, so he won't stop whining. Apologies, no one's beating the dog upstairs or anything like that. Anyway, back to the example here. So it makes sense philosophically. Does it make sense mathematically? Well, yeah, let's see a quick example. So that example on the GRE scores we talked about in a previous video. Population mean was 554. Standard deviation, was 99. Sample mean was 568, and the sample size was 90. So pay attention to that sample size. We're going to plug that into our standard error formula. It goes in the denominator, right, square root of sample size, and that gives us a standard error of 10.44. So when we calculate that Z statistic, we get a 1.34. What about if we change sample size? So everything else stays the same. We get the same sample average, same population mean, and standard deviation. Everything's the same, but instead of 90 for our sample size, we simply increased it to 200 and have the same sample average. Now let's plug in those values. Standard error, now with 200 in the denominator, results in a much smaller standard error. This means that when you put that standard error later into the Z formula, a much smaller number is being divided by, which means a much larger resulting Z statistic, test statistic, which means if we had a 1.96 cutoff value, like we did in the last example, well, a Z of 2.0 passes it. A Z of 1 point whatever it was, here, let's look, 1.34 does not, right? 1.34 is not on the right side of 1.96. It's not significant. You fail to reject the null hypotheses. Right? In this case, the Dearborn students and the population score equally on the GRE. But if we had those same measures of variability, and it was based on a sample size much larger, then we could be confident that our Z statistic of 2.0 was in fact beyond that cutoff value of 1.96. It was enough that we could reject the null hypothesis, even if just barely, and say that it is so unlikely for this difference to occur due to chance that it actually represents a real difference between the sample mean, which represents the Dearborn student population, and the population as a whole. Right? The two populations differ from one another. Okay, so sample size really does matter. That being said, most of our examples, we're going to have super small sample size just so that we can calculate it easily and not have to spend 4 or 5 hours calculating an example with 200 individuals. So, quick review. Random selection. Really important because it makes sure that all those weird things that could occur in the environment are represented equally into your sample, which means it's a representative sample. If you then randomly assign to different groups, it means any of those differences remain roughly balanced between your groups. It means then that you can really start to talk about whether or not the differences between groups are due to the actual independent variable being manipulated, or if they're just due to chance occurrence. How large of a difference do you really need to see to start to say that this is not just chance, right? We talked a lot about the normal distribution, about how it's basically a standardized distribution, and most importantly, that means we know the percentage under the curve at any particular value of that x-axis, right? We typically talk about it right now in terms of Z statistics or Z scores, but we'll introduce T values and other values later on that have a similar sort of effect. What it basically says, I mean, I guess to sum it up, is that most of us are average. So your mom, your dad, your grandma, your grandpa probably at some point told you you're special. The normal distribution disagrees. Right? The normal distribution says, sorry, 68% of us are within one standard deviation above or below. That's 70% roughly of the population are pretty damn close to normal, right? Right in the middle of the distribution. It's only a few of us that end up being so weird or so not weird, whatever the variable is being measured, that we're at the tails of the distribution. That's great, right? That's great because it allows us as statisticians to determine the likelihood of an event. Is this a highly likely event or is this a really unlikely event based on what we know? And then we can simply say, is our sample an unlikely event or a likely event? And if it's an unlikely event, then we can infer something about that population and say, okay, what really was the probability of getting this, given what we know about the population? Low? Then it's not because of chance. It's due to something else, like our hypothesis, right? Okay, so that's the summary, right? That's it. We did z-scores, z-statistics, percentiles. We went into the percentage as extreme or in the tails, really talking about likely and unlikely events. Introduced the z-test, talked about the assumptions of tests and how they're basically robust tests that can stand true even when you bend and almost break the assumptions. But when you do break them, we no longer can run these parametric tests. Parametric because they assume something about the population. And then we run these non-parametric tests that we'll introduce later in the semester. Finally, we went through 6 steps of hypothesis testing. Comparison distribution, stating hypotheses in words and symbols, cutoff values. Those are all the sort of new things we discussed. And then lastly, a discussion of sample size and standard error. So before you...
It is very important that we understand what is meant by the phrase statistically significant difference. We know that significance is indicated by a p-value less than 0.05. But before you go getting all excited about the size of your outcome's p-value, let's be clear about what significance really means. When you find a statistically significant difference, does that mean that there is a 95% chance that the alternative hypothesis is true? Or that this finding will replicate 95% of the time? Or that if the study was repeated, the null hypothesis would be rejected 95% of the time? No. It means none of those things. So what does p less than 0.05 really mean? The p-value is the probability of finding these results if the null hypothesis is true. A statistically significant difference, p less than 0.05, means that the outcome that we observed was unlikely to have occurred by chance. What p less than 0.05 actually tells us is that the results were statistically significant. But it does not tell us whether the results are practically significant. In other words, do these results really matter in the real world? Statistical significance tells us that the treatment had an effect, most likely. But it does not tell us how large that effect was. And finding a p-value that is very small, say less than 0.001, does not make the results, quote, more significant. There is no such thing as being more significant. The results are either statistically significant or they are not. In order to know how large the effect was, we need a measure of effect size. So we may have found an effect, but the effect was really small and of no real-world importance. Measures of effect size will be things like Cohen's d, r squared, and eta squared. Statistical significance tells us to reject the null hypothesis, but it does not prove that the alternative hypothesis is correct. Whenever we make a decision, we could make a mistake. As we learn more about hypothesis testing, it will be important that we not rely exclusively on p-values, but also consider things like effect size, confidence intervals, and the power of our test. We need to think about what Jacob Cohen wrote in an article titled "The Earth is Round," p less than 0.05. What you want to know when you do hypothesis testing is the probability that the alternative hypothesis is true, given the evidence. Did the treatment have an effect? What you get, however, is the probability of obtaining this evidence assuming that the null hypothesis is true. If the treatment really did work, then how likely is it that we would have found these results? Well, the big problem with this approach is that, in reality, the treatment always works. It always does something, even if that something is trivial. And means are never truly equal. If you go out enough decimal places, they will diverge. So the null hypothesis is never actually true. Furthermore, improbable things happen all the time. In fact, if you do enough tests with the same ineffective treatment, some of those means will in fact be statistically significantly different. P less than 0.05 means that 5 times out of 100, 1 time out of 20, we will make a mistake. We will mistakenly identify an effect as significant when in reality it's not. We make a type 1 error. This is also called the dance of the p-values. And finally, statistical significance is a function of sample size. With enough people, every comparison will be statistically significant, even if it is practically meaningless. We must consider the power of the tests that we are running. So statistical significance tells us that the differences that we found are unlikely to be due to chance or luck. But possibly not. And even if the differences are real, they may not mean anything in the real world. And this is why, whenever we run a statistical test, we should also compute a measure of effect size.
Quit and say, okay, I got this stuff. Ask yourself if you truly feel comfortable yet. Could you complete a similar problem on your own, like we just went through there? If I gave you the raw data and you had to calculate a sample average, then you had to calculate, you had to then compare that to a known population mean and population standard deviation. Would you be able to remember to do standard error? Would you know how to determine what the cutoff value was? If not, and you're not comfortable yet with the concept of p-value, alpha level, right, statistical significance, then I'll have another little video you can watch on that as well. But go back and rethink some of this stuff. Watch the video again or practice some more. Can you go back and forth between raw scores, z-scores, statistics, percentages, right? If not, practice it some more. Do extra problems. Go to SI. Come to office hours or make appointments with me individually if you want to. And I encourage you to watch this last video. It's just another example, but it's going to be a little bit more like you might expect on the homework or on the exam, where I give you this hypothetical scenario, the data, and we work through it all from start to finish. Okay? Do all of that, and if you're still not comfortable, do it again with another example and again with another example, because if anything, stats requires a little bit of repetition. It's like a sport in a way. If you don't go out there and practice the sport, you're not likely to improve or remember the basic fundamentals of that sport, right? Or musical instrument. You're not supposed to be going out and playing sports right now anyway. So learn to play violin, and you'll see what I mean by practice, 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 because practice makes what? Amazing?
Awesome.
Awesome. There you go.
Practice makes awesome.
Practice does make awesome. All right, guys. Cheers.